Welcome back to Hardware Security. Today we're going to talk about the vulnerabilities in hardware and hardware design. What you will see next might be pessimistic, but when we talk about security, it's better to be pessimistic instead of optimistic. You cannot and should not trust the hardware you are given, no matter it is a cell phone, it is a laptop, it is a desktop, or maybe it is just a very simple embedded system. There are a couple of reasons behind this. So first, it is the trust issue in microchip supply chain. There might be backdoors in the circuit or in the system. And also, when designers design the system, they have to use third-party intellectual properties. They have to use design tools, which may not come from a trusted source. And the third reason here is, so when people design hardwares to implement applications, implement functions, or implement, for example, crypto primitives, what they consider is performance, not security. So this potentially can introduce security vulnerabilities into the system. Finally, there might be malicious designers, malicious foundries. They may add hardware trojans into the hardware. And in addition to these issues related to the hardware design process, the hardware itself might become a target for attacks, such like side channel analysis and physical attacks. So today we're going to talk about microchip supply chain security and the backdoors, and all the other concerns we are going to talk about later. So let's start with the microchip supply chain. So this figure is coming from a 2006 report from the Defense Advanced Research Projects Agency. It shows the design goes from a user specification, goes to the design team for design, goes to the manufacturer for fabrication, and then eventually deliver back to the system user for testing and for deployment and monitoring. So when the entire design and fabrication phase is in-house, it can be under control. Everything is trusted. However, with the increased design complexity and with the offshore foundry, a lot of these blocks becomes untrusted. So for example, this design team, it may be trusted. We may say, okay, use this design team for years. But however, they are using models which come from other sources. They are using third-party intellectual properties. They are using design tools. And these things may not be designed with a trusted source. And also when we talk about the foundries, these are the overseas offshore foundries. They are out of our control. So what we have here is only the phase when we specify the system, we can trust it. When we get the system back, we can do the test by ourselves. We'll trust our testing. When we deploy the system, when we monitor the system, we can trust this. And everything in the middle, we may not trust it. So now let's come down to see a couple of more concrete examples. So the first example we have is coming from the review slides for digital logical design. So where we have this 3-input encoder. So there are 3 bits input X, Y, and Z, and at any time, any one of them can be 1, but only 1. And what we want to do is we want to encode this with a 2-bit code, which will be fed into the next module as input. So if you remember from the review slides, what we have here is the optimal design looks like this. A is the complement of Z, and then B is the complement of Y. So we know this is the best design. However, there might be a couple of security problems for this design. So first, if we have 0, 0, 0 as the input, following this design, A will be 1, which is the complement of Z. And then B will also be 1, which is the complement of Y. So this overall gives us an output 1, 1 as the code, which coincides with the code for input combination 1, 0, 0. So this potentially becomes a backdoor to the case of input 1, 0, 0. And the second question, well, maybe actually is a more severe problem. So when we have inputs such as 0, 1, 1 or 1, 1, 1, the output of this optimal design gives us 0, 0 as output, which will be fed into the next module as input. But however, if you come back to our system specification here, it does not specify 0, 0 as a potential output. So that means the next module, they may not consider 0, 0, 0, 0 as a valid input. So this may cause some problems for the next module, which potentially can be something called a fault injection attack. So on the next slides, we're going to see an example on sequential system design, where we have a three-state finite state machine. And we have state 0, 0, state 0, 1, and 1, 0. And this diagram shows you that if I'm at state 0, 0, for example, on input x equal to 0, I'm going to move to state 0, 1, and output a 1. So if we follow the traditional design we have reviewed in the review slides, what we have here is we need two flip-flops A and B to encode the two bits 0 and 0, or 0, 1, or 1, 0. And then we need the input, and then we need to specify what will be the next state. Okay? So for example, like the one we have mentioned earlier, start from state 0, 0, on input x equal to 0, I'm going to move to state 0, 1. Okay? So when we follow the traditional design flow, this system can be implemented with two flip-flops like this, A and B, and also with a couple of logical gates here. And what is interesting here is what happens with these two dashes. And when we come back to the system spec, this corresponds to the case that when the system is not specified the requirement. So for example here, 0, 1, that is my current state. And then if input is 0, I don't care where it goes. I don't care what is the next state. But however, from this system here, you cannot generate a don't care. When the system is at state 0, 1, if you give 0 as an input, the system has to direct you to a deterministic state. So when we do a circuit analysis, we find out in this case, the next state will be 0, 0. And similarly, in the other don't care case, the output is also 0, 0, which is the next state. So when you think more about this, you say, okay, now I have two flip-flops, A and B. What happens if both has content 1? So this gives you another state, state 1, 1, which is not specified in the original system specification here. And however, when the system is designed in this way, you must have some next state when the current state is 1, 1. So when we do a full circuit analysis, we realize that when state is 1, 1, depends on the input, our next state can be one of these two states. So this leads us to the following finite state machine model for the system actually was delivered to us, this system here. It is a 4-state machine with everything completely specified, particularly these 4 red edges. And now you say, okay, so this 3-state machine is what I want. I want you to design a system for me to do this functionality. And this is what is delivered to me. And if I check, all these original constraints, they are met. So this is a system that works for me, but however, I may not trust it because it also implements all these edges in red, which I put question marks here. So this is something we call the backdoors. And then they can potentially create vulnerabilities into the system. So for example, now we see this finite state machine, it is what we required, and then this is what delivered. And we mentioned that we may have these backdoors here, and then how can we figure out these backdoors? Well, how can attackers find these backdoors? So we consider this simple case where we assume that state 0, 0 is a state that we want to restrict the access. So in the original system, nobody can come back to 0, 0. There's no incoming edge coming into 0, 0. But however, in this new state, or this new state machine which have been implemented, I do see these edges coming back. I do see this one coming back. I do see this one coming back. And then for state 0, 0, I can go to 0, 1 and then come back. So in the state machine that I have in the design, everybody can come back and access state 0, 0. So this is the potential vulnerability. But how easy it is for the attackers to find this backdoor. To show this, we designed a very simple random walk attack. So in this attack, the attacker is going to start from a random state, for example, 0, 1. And then he is going to try a random input, for example, 1 again. And with this one, the system will move him into state 1, 0. And then he will say, okay, so this is not what I want, not state 0, 0. So he's going to try another random input, for example, 0, 0. And then this one stays at state 1, 0, still not the target 0, 0. And next time, the attacker is going to try input 1. And this will take him directly to the state 0, 0, which means that the attacker now have access to the state 0, 0, which he doesn't have access, or which he should not have access. So now we use the same example to show, how malicious designers, they can introduce hardware Trojan into the system. So, for example, in this case, again, we want to limit the access to state 0, 0. And then malicious designers may say, okay, so I want to have a backdoor access to it. And how do I do that? So what the attacker can do is, he can simply specify all these unspecified conditions, direct them into the state 0, 0, which is the one he wants to get access. And for this hidden state, which is not specified, he can also specify them go to this state. So whenever the system is in any of this state or this hidden state, and the attacker can give an unexpected input, and then the next thing they know is they're going to have access to this state. So that is a very simple way to gain unauthorized access. And if you know that the attackers can do this, we can do some very simple countermeasures. So for example, I realize these are the potential vulnerabilities. So how about I put all these things back to a state which is safe? Safe in the sense that this one cannot go back to state 0, 0. So in this case, you do have 100% trust, or you do have 100% security. But however, there is a huge design overhead, which normally we cannot afford.